Okay, so in this problem, we're asked to find the angular velocity omega OA of from this length over here, from this length OA, and the only thing that we're given is this velocity over here. So what we're going to do is we're going to first look at this link because it has the most information in terms of velocity and stuff. Like, we actually have a value that we can work with, and then we're going to transfer all that information into point A, and then since these two links are attached by point A, we're going to use point A as like a source of information to then solve for the angular velocity at length OA. Okay, so first thing we're going to do is we're going to write our relative velocity equation for AB. So we're going to say, you can write it anyhow, but I'm just going to say VA is equal to VP plus VA relative to B. Okay, and we're going to first solve this problem algebraically, and then we'll solve it using a vector triangle. So we're going to solve with this equation here, and then because A and B are on the same rigid body, right, so I can draw this link separately. We have B, we have A, and VB, and since these 2 points are on the same rigid body, we can then break down their relative velocity term into omega AB crossed with R A relative to B. Right, cool. So we can then start checking our unknowns and see how much information we have to solve this problem. So we can find that we know this, we don't know that, and this is what we're trying to solve for. So we have two unknowns, one equation. So okay, let's go look at the other link. Let's look at the link AO and see if we can, because we can write an equation for VA, right, in terms of O, and then let's see if we can relate the two somehow. So we're going to say VA is equal to VO plus VA relative to O, and then since O is a fixed point, its velocity is 0, then VA is just equal to VA relative to O, and then this becomes omega AO crossed with R A relative to O, right? So we can find that, we don't know this, we're trying to solve for that. Cool. So we can write this as one equation. We can equate the two VAs together and write this as a log equation, and we'll get omega AO crossed with R A relative to O is equal to velocity of B plus omega AB crossed with R A relative to B. Cool. Then we can solve that. We don't know this, we have that, we can get that, and we also don't know that. Sorry, we can get this. Yeah, cool. So we have two unknowns, but secretly we have two equations, right? We have, if we break this down into its x and y components, we can solve for it. So this will give you, this term over here will give you omega AO, right, multiplied into something I hat plus something j hat, right? And then that will equal to VB, and VB is only acting in the j direction. So you're going to have minus VB, in the j direction, plus then again omega AB. That goes into something I hat plus whatever j hat, right? Cool. Then what we're going to do is we want to equate our i's together and we equate our j's together, and then you can solve simultaneously to solve for omega AO. So that's one method of solving the question. Another method of solving the question is using a vector triangle. So we're going to take the same approach where we start with this equation over here. So again, we're looking at this length over here, and then we're going to break it down into its into this form over here, right? Cool. And then we're going to try and construct a vector triangle using this equation. Okay, so what I like to do when trying to construct the vector triangle, I like to draw whatever linkage or whatever body they gave to me in the question. So for this case, I'm looking at linkage AB, and I want to try and draw my velocities from that. Okay, so I have point A over here, I have point B over here, and I know that my velocity of B is going straight down, right? So I'm going to draw that in at point B. This is my VB. Cool. Then velocity of A from the linkage AB, I don't know how the velocity of A is going to act, right? Because point B is pulling this whole bar downwards, right? And the velocity of A itself is going to manipulate the bar, the motion of the bar in some other way, right? And I don't know how to quantify that, right? So what I'm going to do is I'm going to resort to linkage OA to try and get the direction for the velocity of A. So I'm going to draw in OA over here. So I have point O, have point A, and then I know that this is going through fixed axis rotation, right? So point O is stationary, and if you know about fixed axis rotation, right, I can write my equation for this. I can say that VA is equal to VO plus VA relative to O, right? Then we know that VO is 0 because it's a fixed point. Then VA is going to be equal to omega AO crossed with R, A relative to O. Cool. So over here we have the cross product between two vectors. The cross product between two vectors always results in a vector that is perpendicular to both of those two vectors. So I'm going to get a vector that is the result of this, which is VA over here. The result of this cross product is VA, and it's going to be perpendicular to whatever omega AO was and whatever this RAO is, right? So omega AO points out of the page, right? So we have our Y, our X axis, and then our Z axis pointing out of the page. Omega AO points in this direction, in the Z direction, right? So already by default, if I draw my vector anywhere, if I draw like VA in that direction, it's already perpendicular to the Z axis, right, by default. So the only rule we have to then obey is that VA needs to be perpendicular to RAO, right? So VA, in simple terms, VA will be perpendicular to the do you call this vector? The position vector, OA. And this is true for any case of fixed rotation, fixed axis rotation. So whenever you have fixed axis rotation, like this, right? Let's say you have something like that. The velocity of any point here, so could be that point, could be that point. All of these points will have a velocity that acts perpendicular to the position vector. The only thing that will change is their magnitude. So the further away you get from the center of rotation, the larger the vector will be, right? So cool, we've now figured out the direction of VA. I'm just going to draw it in again. So I have VA here, and I know that it's perpendicular to AO. Cool. So on my diagram over here, I'm going to draw in AO just so I can reference it when drawing VA. Cool. I'm going to draw it in like that. And then I know that VA is either going to go down or it could go up, right? We don't really know. You could kind of like try and visualize this problem and see that AB, right? Since B is moving down, then this will kind of move, if I can get this ruler to move nicely, this will kind of move down like that, right? And then this OA, what's going on? OA, right, will move like that, right? But you don't need to be able to see that, and that might be incorrect. I don't really know for sure. You don't really need to see that. So what we do is we say, okay, A could either go, VA could either go up or it could go down. The only rule that we have to obey is that it must be perpendicular to OA, right? Cool. And then if we look at this equation again, we've taken care of VA, we've taken care of VB on our diagram, so we have VB, VA. The next vector we need to take care of is VA relative to B. So VA relative to B, remember we broke it down into omega AB crossed with R, A relative to B. So the same thing applies here. So you have cross product of two vectors, and the resultant vector of this, which is going to be VA relative to B, needs to be perpendicular to this position vector RAB. So I'm just going to draw it in over here just so that we don't get confused. So we're going to have VA relative to B, and again it could either go up or it could either go down. Cool. Then when drawing our vector triangle, we're going to look at the vector. What I like to do is look at the vector that we know the most information about. So we know the direction of VB and we know its sense. So the sense, like where, kind of like its angle of rotation, if that makes sense. So it's pointing, it's in the vertical direction, that's its sense, and then its direction is downwards. So yeah, hope that makes sense. So VB is like that, and then this vector equation, I'm just going to write it again. VA is equal to VP plus VA relative to B, right? So what this equation is telling us is that VA, so we always read this from left to right. So we're going to start with VA. VA must start at the tail of VB and end at the head of VA relative to B. Okay, so must start at the tail of VB and must end at the head of VA relative to B. So VA is going to start here, and depending on VA relative to B, it must end at the head of that vector, right? So what I'm going to do is I'm going to draw VA, because we said it could either go that way, right? Let me just draw it at a steeper angle to more closely match our diagram. So it could either go up or it could go down, right? Cool. And then we know that it must end at the head of VA relative to B. So I need to choose the direction of VA relative to B such that the head of this vector ends at the head of VA, right? So I'm either going to choose my direction. Also, I need to close the triangle, right? So I can't choose the vector to point this way because it's not going to close the triangle. So in order to close the triangle, it needs to be this way, right? I hope that kind of makes sense. Okay, so VA relative to B is automatically going to be over here, right? And I know that VA needs to end at the head of VA relative to B. So I'm going to draw the arrow in this direction. So VA must end over here. Okay, so hopefully that makes sense. Okay, and then what we need from this, if we can find VA, right, then we can plug this into the equation where we analyze A relative to O, and we just found that VA is equal to omega AO crossed with R A relative to O. So if we can find VA, we can solve for the angular velocity that we're looking for, right? So cool, let's try and look for angles that will help us get VA. So whenever looking for angles, look for a vector that is either vertical or one that's horizontal, right? And then use this diagram to help you find the angles that match your vector diagram. Okay, so I'm first going to define angles that are made between one vector and a vector that is either vertical or horizontal. So I have a vector that's vertical, so I'm going to call this one alpha and I'm going to call this one beta. Okay, so those are my two angles that I'm going to try and look for. Cool. And then take note of the vector that you're making them with. So I'm going to look for VA relative to B, and then I've also made the angle with VA. So I need to draw those in my diagram and then look for those respective angles. So I'm going to start with VA. Just going to delete this. So VA, I can reference VA with link OA, right? Because I know that VA must be perpendicular to this link, right? Should be like that. So cool. I'm going to draw in that link, point O, have point O, have point A, and then I know that VA acts in this direction, right? And then I know that's 90 degrees. And the angle that I'm looking for is the angle that A makes with a vertical vector or a vertical line. So I'm going to draw the same vertical line over here, and I know that this angle, whatever it is equal to beta. Okay, so if I can find this angle, then I can find, well, I'm going to need to do a bit more work, but then eventually I'll be able to solve for whatever VA is, right? So, cool. On my diagram, I'm going to match what I have over here. So already over here, you can see that we have a right angle triangle, right? So I'm going to draw the exact same thing over here. Okay, cool. Then in my right angle triangle over here, I'm going to call this angle theta, and then I don't know, I'm going to call this like theta prime or something. Cool. So if I can solve for theta over here, then I can use the sum of angles in a triangle to solve for theta prime. And then I can take note that theta prime is literally just this angle over here. And then 90 minus theta prime will give me beta. Okay, which is what I want. So to get that, I first need to solve for theta. And then if you look at this whole thing is just a triangle, right? And they gave you all the sides of it, right? So you have theta that you're trying to solve for, and you have this big triangle, right? Which looks something like this, with this being 180, 90, and 130. And you have theta there. So you can use the cos rule to then try and solve for theta. And then once you have theta, you can find theta prime using sum of angles in a triangle, and then 90 minus theta will give you beta. Cool. Then for the next vector, we have VA relative to B. And I know its direction. I know that it's going to be perpendicular to link AB, right? So I'm going to go and draw that link. I'm going to draw link AB. So I have point B there, point A over here, and I know that A relative to B is going to be perpendicular to that, and I'm just going to draw it here. Right, and I want the angle. Remember, it's making alpha as an angle between the vector VA relative to B and a vertical line. So I'm going to draw in a vertical line over here, and I know that whatever angle is over here is going to be alpha. Cool. Now I can extend this out if I want. Maybe it will help, maybe it won't, I have no idea. Okay, and I know again that this is still 90 degrees. Right. Cool. So then again, if I look at this, I have another triangle. And again, if I can solve for this angle, right, let's call this phi, and let's call this phi prime. If I can solve for phi prime, then I can solve for whatever alpha is. Okay, so if I go to my big diagram over here, right, I have phi on this side, And then this is the triangle that we drew over here. So you have point A, point B, point A, point B, and then we've made a vertical line. So over here, sorry, this is phi, and then this would be phi prime. Cool. So if we can solve for phi prime, then we'll just say that 90 minus phi prime is equal to alpha, right? Cool. So again, we can use cos rule, but then this time we're looking for phi, right? So we use this triangle, apply cos rule, solve for phi, and then we can use sum of angles in a triangle to get phi prime, and then 90 minus phi prime will give us alpha. And then once we have those two angles, then we can use sine rule. So we can use sum of angles in a triangle first to solve for this angle here, and then we can use sine rule because we know what VB is, and then we've solved for alpha, we can find VA, and then you just simply use VA relative to VO to then solve for omega OA.